Um, all right, let's go ahead and get started. Same deal as last time. You guys got some homework due this Sunday. I'm going to leave those up for Sunday, sections 1 through 4, but I've decided to make the homeworks due on Fridays from now on, mainly because I was looking and not a lot of people have started the homeworks yet, which makes these meetings kind of dull. So I really want you guys to try to work on the homeworks before we come to these meetings. That way you can ask questions when you get stuck on something. So next week's homework, sections 5 and 6, I have due for that Friday on the 5th instead. After that, we're going to be done with chapter 6, and then I'm going to have the test due probably shortly after this section 6 homework is due. So I haven't quite put a date on it yet, but I'll be doing that pretty soon. It's still a week or so away. Other than that, we got an hour. There's a couple of questions that I really want to go through with you guys, just because I think they're pretty hard, and I think it'd be good for you to see them. But before I pick the questions that I want to show you, are there any questions that you want to see?
I have one.
Okay.
It's 162 for 5.
Okay, yeah, we can look at that one. So find the volume of the solid generated by revolving the region blank about the y-axis. So it gives us a lot of bounds here. So let's kind of graph that out. I know it's hard to graph these when it's solved for x instead of solved for y. You have a couple of different options here. One option would be to interchange the x and the y value and graph it like that, and then just rotate that around the diagonal line. You're kind of graphing its inverse instead. Another way of doing that is just to graph it in Desmos instead. So if I pull up Desmos here, just to show you what this graph would look like. It was x equals root 35 y squared. So you see Desmos will graph it pretty easily. So if you're working on your homeworks at home, then of course you can just do this. So just looking at this graph and then the other bounds, x equals 0, that's going to be the y-axis. Y equals -2 and y equals +2 are going to be two horizontal lines. You can graph those in Desmos as well. All right, so you have to be careful about the region that we're looking at here. We're not looking at the inside of the parabola. We're actually looking at the outside regions. So in between the blue line and the red line and the y-axis, this kind of triangular-ish looking region, and then this one down here as well. And then we're rotating this or revolving that around the y-axis, I believe. Yeah, the y-axis. Okay, so to do all that, we first need to decide which method we're going to use. We really have 3, the disk method, the washer method, and then the shell method. Sometimes all 3 of them would work, sometimes only one of them works. It's just kind of looking at the question and figuring it all out. Before you decide which method to use, you should probably decide whether doing vertical slices or horizontal slices are going to be easier. And it all depends on where those slices start. So if we're just looking at this top region here, if I were to do vertical slices, it would work. My top would go from 2 down to the bottom would go to the parabola. But that's a little bit difficult to define. It would be a little bit easier if we did horizontal slices instead. Because every horizontal slice is going from 0, from the y-axis, up to the parabola, and we already have the parabola solved for x. Also, since we're revolving this around the y-axis, that means that my region is bordering my axis of rotation, which means that we can use the disk method. So we're going to use the disk method for this one. We just have to be a little bit more careful with it because we're revolving around the y-axis. It's not going to be an integral with respect to x. It's going to be an integral with respect to y. So the integral of pi, and then my radius as a function of y squared. Okay, we just have to figure out what that radius is as a function of y. So let me go back over to the graph. If I have horizontal slices and I rotate those horizontal slices about the y-axis, I'm creating my discs. The radius of those discs is just going to be the length of my slices. The length of the slice is going from 0 to the parabola, which has a horizontal distance of the square root 35y squared. So that is going to be my radius. Other than that, we just integrate over that. So we're just going to do the integral. We'll come up with the limits here in a second of the square root 35y squared dy. The limits are going to be where your slices exist. So going back to the graph, we're going to have horizontal slices from the green line all the way up to the blue line, going from 0 to the parabola every single time. So we're going from -2 to 2 on the y-axis. All right, and then just to do the integral here, so we're going to take that y squared, raise it up to y cubed, and then divide. So we still have that square root 35. We're going to take that and divide that by the 3. We have the y cubed, and then we're evaluating this from -2 to +2. So if I plug 2 in there, I get 2 cubed is 8. So I have 8 square root 35 divided by 3. That's going to be minus plugging -2 into there, which is going to give us -8 square root 35 over 3. The double negative says to add these two things together, so that's going to be 16 square root 35 over 3. And that should be it. That should be our answer here. I'll just go over and plug it into the homework, make sure we're right. 16, how do you do a square root in this? Yep, 35 over 3. Oh no, I goofed. I messed up somewhere. There's some little mistake here that I don't see. Oh, I forgot my pi. That's what it was. Somewhere I dropped the pi along the way. Nope, that wasn't it either.
Does the 16 need to be up top with the root 35?
It shouldn't matter. Do I need to what? Sorry, I couldn't hear you. Square? No, because it's cubed, right? I already cubed the 2. Oh, up here. You're right. I was going too fast. I see what you're saying. Yeah. We were supposed to square the radius, so all of this was nothing. It was supposed to be this radius, the root 35y squared, all squared. Good catch. And then the pi should still be out in front. Okay, when you square that, then we're going to have the integral. Still have the pi. Still from -2 to 2 of just 35y to the 4th dy. All right, so that's going to have antiderivative of just 7y to the 5th. That we're going to plug in 2 and then minus plugging in -2. So 35 times 7, whatever that is. I have a calculator here. $245. So it's going to be 245 and then minus a -245. And then my pi should still be floating around somewhere as well. So 490 pi. We'll try that instead. I can't do math today. Today's not my day. But we're closer. I must have done some other little mistake somewhere. I don't know now. I don't know where I went wrong. Oh, I know where I went wrong. I didn't plug a 2 into that, right? Sorry. I'll slow down from now on so I don't make so many mistakes. I think that should be 175 when you plug the 2 into there. Or... no, that doesn't come out right either. Sorry, 224. Oh, man. There we go. So yeah, that doubles to be the 448. So that was my calculator's fault. I'm not going to take blame for that one. I definitely hit the right button. It just didn't show up right. So 2 to the 5th, that's going to be 32, right? And then 32 times the 7 is 224. Which gives us the 448 pi. So besides all those little mistakes that I made, does that make sense on at least setting the question up correctly?
Yes.
All right. Is there any other homeworks that you guys want to look at? And I promise I won't mess this next one up.
Are you able to look at number 15?
Yeah. So there's a lot of parts to this one. Let's at least start it off with the first 2 maybe, and then we see how we feel after that. So use the shell method to find the volume of the solid generated by revolving the region bounded by the line y equals x plus 6 and the parabola y equals x squared. Let's look at x equals 3 first. So I'm going to go in Desmos again to graph these. So we have the 2 equations and then the axis of rotation. So y equals x plus 6. We also have the parabola y equals x squared. So there's my region that we're going to be revolving. First, we're revolving that around the line x equals 3, which is this red line here. So we're going to be revolving it to the right to make our solid. Whenever you're doing the shell method is when you make your slices to create cylinders instead. You always want your slices to be parallel to the axis of rotation, because when you revolve a parallel line, it creates the cylinder or the shell. So our slices are going to be defined above by the diagonal line and then below by the parabola, and they're going along the x-axis. Okay. Because we're doing the shell method, let's at least get the formula for the shell method written down. That's going to be the volume is the integral from wherever we need to go to wherever we need to go of 2 pi, the radius of the shell times the height of the shell. Because for part A, we're going along the x-axis for my slices, it's going to be dx. So we need to come up with the radius and the height as a function of x. Okay, so going back over to the picture, we need the radius and we need the height for wherever we're located. Let's say for now, my slice is going right along this dotted line here. So this is going to be located at x. It's really located at 1, but we're just going to call it x for now. The radius of the slice or the cylinder is going to be the distance from your slice to the axis of rotation. So you have to be very careful here. If the slice is located at x, then the radius has to go from that location x to the axis of rotation, which is here at 3. So if my x was located at 1, I would need it to have a radius of 2, which means to find the radius, we're going from the axis of rotation minus the location of the slice x. So the radius of my cylinders is going to have a distance 3 minus x. The height of the cylinders are going to go from the diagonal line down to the parabola. That distance we get just by subtracting those two values. So my height is going to be the diagonal line, which was x plus 6, minus the parabola, which was x squared. And then we can simplify that down to be negative x squared plus x plus 6. Okay, now you just take your radius and your height and you plug them into the integral here. So we'll come up with the limits here in a second, but we're going to have the 2, we're going to have the pi, we're going to have the radius 3 minus x, and we're going to have the height, the negative x squared plus x plus 6. All right, the limits are going to be where your slices exist. Our slices are going to exist from this intersection point to this intersection point. So this point right here is at negative 2 on the x-axis. We're going from negative 2 all the way to 3 for all of my vertical slices, everywhere in between the diagonal line and the parabola. So negative 2 to 3 for the limits. Okay, so that's just setting up the integral. Is there any questions about where I got any of that before we do the integral? Okay, moving on then. So let's pull the 2 pi out, and then we're just going to have to multiply those two things together. So I don't know how you guys do it. I've seen a lot of different ways of multiplying polynomials like that. I usually just take the 3, multiply it by everything, and then the negative x, multiply it by everything. So the 3 times everything, and then the negative x times everything. All right, we'll combine all the like terms together, and we'll do our antiderivatives. All right, so antiderivative for each of those is just a power rule. So make sure all of that makes sense to you. Ask questions if you have questions about that step.
When you get to that part there, how do you put that in calculator?
I do it one step at a time. So I would just plug the 3 into here, get that number, plug the 3 into here, get that number, 3 into there, get that number, 3 into there, get that number. You could do it all in one go, but you would have parentheses everywhere. So if you're okay with that, then I'm okay with that. Some of you I know have like super fancy calculators. If you have a super fancy one, you can just plug it in like this with the x's, and then you can just set x is equal to 3 and it'll give you the final answer. All right, so plugging 3 into all of this stuff really carefully. We have the 2 pi still on the outside. 3 to the 4th is some really big number. So we're going to have an 81 fourths minus, that's going to be 36, I think, minus 27 halves plus 18 times 3. 54. Okay, that minus 2 pi times negative 2 into all of that stuff. So 4, negative 8, positive 32 thirds, I think. Okay, I tried to just do that mostly in my head, but then we get that, and then just combine all the numbers together. So I got this 625/6 pi. If one of you was using the calculator as well, let me know if that looks right. I'm scared to plug it in because I already got one wrong today and I don't want to get another one wrong today. I'm going to do it. I'm going to hit enter. Oh, yay. All right, so we got the green check mark. Okay, so this was just part A. Let's at least set up another one. We'll do part B and part C here. But is this all right? Is there any questions about this one? Okay, if not, let's try part B. So part B is revolving around x is equal to negative 2. So if I go back in Desmos, instead of x equals 3 for the axis of rotation, now we're going to be doing this red line, x is equal to negative 2, and revolving it to the left instead. Almost everything is pretty much the same for part B here. The only difference is how the radius is going to be defined. So let's look at the radius as a function of x, and then we'll just bring down the height as a function of x, because that's going to be the same. The height is still that negative x squared plus x plus 6 that we had found from here. The height is the same because we still have a vertical axis of rotation, which means that my slices are still going up and down. Now the radius is going to be a little bit different. If I am located at a vertical slice at x on the x-axis, I need to find the distance from that x to the location negative 2. Now there's a couple different ways to do it. The easiest way, I think, is just going to be x plus 2. Right? Because if I'm, wrong thing. If I'm located here at 1, that means that I'm a total distance of 3 from the axis of rotation. So we're going to take that 1 and then add the 2 to be x plus 2. And you can try other ones as well. If you're here at negative 1 and you add 2, you're only going to be at 1, which is where you should be, the distance from the axis of rotation. So I did x plus 2. I'm sure there's another way you could write that out, though. Is that okay? Does everybody understand where I'm getting that radius from? The distance from each slice to the axis of rotation is the radius. And then we just plug that in. So it's going to be another integral, the same integral. We're still going from negative 2 to 3. Oops, sorry. Since that's where my slices are going to exist. And it's still going to be 2 pi times the radius x plus 2 times the height negative x squared plus x plus 6 dx. And you just do this integral the same way. I'm not going to bother doing it because I'm sure you guys can multiply stuff together and then do antiderivatives. It's just cumbersome. But, you would have to do that part. Is that all right, just setting part B up before we look at part C? Because part C is way different. Okay, I'm trusting everybody. That everybody's okay and there's no questions. Okay, great. Here you go, part C, because part C is going to be kind of weird. For part C, we're revolving it around the x-axis instead. So going back over to my graph, we're not doing x equals 2 anymore. We're doing the x-axis y equals 0. So this blue line down here. If you were going to do the shell method, you would have to do horizontal slices because your axis of rotation is horizontal. The problem with horizontal slices is that your slices would be defined differently as you moved up your area. Initially, your slice would go from the parabola back to the parabola. But once you got up here at y equals 4, it would be going from the diagonal line to the parabola. It is still possible to do the shell method, but you would have to do two separate integrals from 0 to 4, and then do it that way with this definition for the radius and the height, and then from 4 up here to 9, and have a different definition for the radius and the height for that top part of the area. I know the homework says to do it using the shell method, but do not do part C and D using the shell method. It's just too hard and too much work when the washer method is so much easier. So instead of doing these horizontal slices, vertical slices are still easier, and with vertical slices we're going to be doing the washer method for part C instead of the shell method. Remember that the volume for the washer method is the integral from A to B of pi, and then it's the outside radius squared minus the inside radius squared. So we have to define the outside radius and the inside radius, and they're not hard to define, especially for this question. If my axis of rotation is down here, the x-axis, the outside radius is the diagonal line. The inside radius is going to be the parabola for my vertical slices. And then that's it. So my outside radius was that diagonal line, x plus 6. My inside radius was the parabola, which was x squared. Then if I plug those into my integral is still going from -2 to 3, since that's where those vertical slices were located. The pi, the outside radius x plus 6 squared, minus the inside radius x squared dx. And then the same thing, right? It's not hard, it just takes a little bit of time. You would square out x plus 6 and then square this one. Let's just go ahead and do this one just to get a little bit more practice. And to see if we're getting the right answer. So I'm going to pull the pi out of the integral. We're going to square x plus 6, which is x squared plus 12x plus 36. X squared squared is x to the 4th. There's nothing that we can combine here, so I'm just going to go ahead and do the antiderivative. Again, just power rule stuff for these, raising the exponent up by 1 and then dividing by that exponent. And then we're going from -2 to 3 again. So plug 3 into all of that stuff, minus plugging -2 into all of that stuff. I'm going to use a calculator this time because it's too much work. So we still have the pi, and if we plug 3 into everything, we get 9 plus 54 plus 36 times 3, I think is 108. Yep. Minus 3 to the 5th, 243 over 5. Okay, that minus the pi on the outside and then plugging -2 into all of this stuff. Great. And then just add all that stuff together. I got this 500 pi. Just plug it in to see if it's right. We got to get to, we got to get to part 3. So I'm just going to get part 2 wrong a few times. If you needed the answer for part 2, it was 625 pi over 6. Same thing as part A. Just coincidence. It's not going to always be that. And then part 3, we got 500 thirds pi. And then, yeah, green check mark. Okay, so even though it says to do it with the shell method, definitely don't. Too hard. Not worth it. And then part D, you would do the same thing. So part D, we're going to be revolving around the horizontal line y equals 9, which is way up here. You just do the same thing. It's just going to be a little bit different because now the outside radius is the parabola, and then the inside radius is the diagonal line. Just be careful because the outside radius has to be the distance from the axis of rotation down to this. So it's going to be 9 minus x squared. The inside radius 9 minus the x plus 6 to get the inside radius distance. But it's still the same concept as what we just did here. Alright, yeah, definitely a hard question. Took us a while. But does that help at least get you started on this question?
Yeah, I do.
Awesome. Okay. Any other questions from this homework or the next? Okay, so I'm just going to pick out, there's 2 questions that I really wanted to show you guys, just because I think they're very hard, and I don't want you to get stuck on them when you do work on the homework. The first one is this, which is number 8 on this first section, the hemispherical bowl question. So we'll do this one together. A hemispherical bowl of radius A contains water to a depth h. Find the volume of the water in the bowl. I'm going to go over to OneNote here so I can draw the stuff out. Let me get my pen working. Before I get started on this question, I want to show you guys something funny. So in OneNote here, whenever you write stuff out, it tries to title the page. So I was working on a video earlier and it titled it Pretty Lady. I don't know how they got Pretty Lady out of any of this stuff. I thought that was hilarious. This one I get, right? This one's called Bucket because the first thing I wrote was bucket. This one's called Natural because I put natural, right? But this one's called Pretty Lady. I have no idea where they got Pretty Lady out of any of this stuff. Like I can kind of see it, right? Like right here. Oh no, my pen's not working. Here. Right? This kind of looks like lady. A little bit, right? I don't know where they got pretty out of any of the other stuff. I thought it was hilarious. Anyway, moving on. Let me see if I can get my pen to draw, though. You'll need a new app to open this OneNote. All right, there we go. We're going. Okay, so going back to the question. We have this, right? We have a hemispherical bowl of radius A contains water to a depth h. Find the volume of the water in the bowl. So a hemisphere is just half of a sphere. So we have this. The total hemisphere has a height of A, right? Not h, sorry, that's the water. So this goes up to A, but the water in the bowl is only at h. Okay. What you need to do for this question is first you need to make your origin. I think it's easiest to put the origin at the bottom of the bowl. Then the bowl goes up to A, and then it has the water located at H on the bowl. You might also want to put the origin at the top and try it that way if you like it that way. The first thing that we need to do is that if we're trying to find the volume of the water inside of the bowl, is we need to come up with the formula for the outside of the bowl. And that's coming from the circle, right? Because it's a sphere projected onto the two-dimensional plane here. So we need to write out the formula for a circle. And this is the formula, right? It's x minus the h to the center squared plus y minus the k of the center squared is equal to the radius of the circle squared. This h here has nothing to do with the h of the top of the water. It's a different h. This hk represents the center of your circle. Okay, so for our circle, the center of it is here, located at 0a. So we have an h of 0 and a k of a. So we get this as our formula. Just x squared plus y minus a squared is equal to the radius is also a squared. Okay, so we'll come back to this here in just a second. Let's kind of talk back through it a little bit. This really is a three-dimensional object that we're looking at, right? This sphere. And we can find the volume by doing that revolution stuff we were doing before. If I look at this area here beneath the water down to the edge of the bowl, and I revolve that around the y-axis, I get the total volume of the liquid. So if we want to find that volume, we need to come up with a method, either the shell method or the disk method or the cylinder method. It doesn't really matter. I think the disk method is going to be easiest to do here because our area is bordering our axis of rotation. If I am going to do the disk method has slices that are perpendicular to the axis of rotation. So I'm going to redraw that picture a little bit, but just what we need. All that we need is just this shape here, where this is the top of the water at H, and then we have the bowl coming down to the origin. If I do make these horizontal slices, each horizontal slice is located at Y on the axis, and then my disk method has the formula that the volume is the integral of pi times the radius. It's going to be a function of y this time, squared dy. Okay. This radius as a function of y is going to come from the formula for this circle here. I have to have it solved for x. That way it's a function of y. So I'm just going to subtract this y minus a squared over. So copying down the circle formula, x squared, we're copying it and subtracting it over. So we have the x squared, the a squared is on the other side, and I'm subtracting that 1 minus a squared over to the other side. And we can simplify this down by foiling out this. And we get this. Minus a squared. So that's just foiling out this 1 minus a squared and then distributing the minus sign. Then the a squares cancel, and we get this. So x squared is equal to this, which means that x is going to be the square root of that. I'm not going to worry about the plus and the minus of that square root because we're in the positive x direction on my graph anyway, so the negative's not going to make sense. This is going to be the radius. Right? So the radius as a function of y, not a function of x, sorry. Radius as a function of y is this square root here. So we're just going to plug that into my formula. because it's the square root and we're squaring it, it's just going to cancel out. So the total volume of the liquid is going to be the integral. We'll come up with the limits in a second, of pi, and then the square root squared, which is just the inside, the negative y squared plus the 2ay dy. Okay, now let's talk about the limits. The limits are going to be where all of the slices exist, and the slices are going to exist from 0 all the way up to the top of the water, which is at h. So we're going from 0 to h for the limits. Okay, I did a lot there, right? This is a hard question, and I know it's a hard question, and I know I did a lot of weird stuff. Kind of weird. But is there any questions on how we set any of that up? So far? And if you need me to scroll around to see something that I've written up here, let me know. Man, looking at it, the handwriting's so bad. Sorry about that. Is this all right so far? Is there any questions about any of this before I keep going? Okay, great. So antiderivative, pulling the pi out, we get negative 1/3 y cubed plus here ay squared. And then we're evaluating that from 0 to h. Plug the h in. We don't have to worry about plugging 0 in because it's all just 0. So we still have the pi, and then it's going to be negative 1/3 h cubed plus a h squared minus 0. You can distribute the pi in if you really want to give us a negative pi over 3 h cubed plus pi a h squared. Okay, I'm going to go back over to Word and just write this result that we got. Let's first, I guess, type it into the homework to make sure that we got that right. So the volume of the water is negative pi over 3 h cubed plus pi a h squared. So yeah. And that should be the same for everybody, right? Because that doesn't really change. Only the numbers will change. Okay, so that's how we found the water, the volume of the water in the bowl. We found kind of a cross-sectional area of it, and then we used the disk method with the volume of revolution stuff that we were doing with the disk method. Okay, part B is stuff that you learned back in Calc 1. So if you believe this, at least, part B, water runs into a sunken concrete hemispherical bowl of radius 5 at the rate of 0.2 cubic meters per second. How fast is the water level in the bowl rising when the water is 4 meters deep? So going back over to Word and kind of copying what we have down here. All right, so what we have, get to a fresh page, is we have that the volume of the water is that answer, that negative pi over 3 h cubed plus pi a h squared. What this next part is asking us to do is that we want to figure out how fast is the water level in the bowl rising when the water is 4 meters deep and we have a bowl of radius 5 that we have water running into at 0.2 cubic meters per second. Anytime it's asking you how fast is something happening, that's talking about a derivative. How fast is the water level rising? Well, the water level we denoted with h. So to figure out how fast is the water level rising, we have to find the derivative of h. The problem with that is that this is not solved for h, which means to find the derivative of h, we have to do something that you learned back in Calc 1, which has a name, and it's called something. What's a funny derivative called? Oh, I can't think of the name of it. You know when you have to take the derivative of both sides, with a different variable. What's it called? I can't believe I can't think of the name of it. Whatever it's called, we're going to do it, right? So what we're going to do is we're going to take the derivative. Implicit differentiation. Thank you, Jeffrey. Yes. Implicit differentiation is what we need to do. We're going to take the derivative of both sides with respect to t. Right? Because if we want to know how fast something is doing, we want to take the derivative with respect to time to figure out the speed with respect to time. All right, some of this stuff is changing with respect to time and some of it is not. So when we do the implicit differentiation, we just have to be careful. The volume of the water is changing with respect to time. So when I take the derivative of the left-hand side, the volume is going to be a derivative with respect to t. So we're just going to have to leave that as dv dt for now. On the right-hand side, the h, the height of the water, is also changing with respect to time. So we're going to have to do an implicit differentiation here, which means to do like a chain rule. We're going to take the derivative with respect to h and then multiply that by dh dt. So we're going to bring that 3 down, which is going to cancel out with the 3 that's already there. It's going to be a negative pi h squared, and we have to multiply that by a dh dt on the back of it. So it's going to look like that. Same thing with this other one. Remember that A was just the radius of the bowl, and the radius of the bowl is not changing with respect to time. So that's just a constant that's going to stay there. We take the derivative with respect to h, which is just going to bring down the 2 and leave the h as a 1. But again, we have to multiply by a dh dt on the back of that one. Okay. We're trying to solve for this dh dt, so now I'm going to factor it out of both of those terms. I'll just pull it to the front. So just factoring the dh dt out of the front of those two terms. Usually at this point, what you would have done in Calc 1 is you probably would have divided this over to the other side to get the dh dt on one side by itself. But we don't need to do that because we're just going to plug in numbers. So going back through the question here for part B, water runs into the tank with the bowl of radius 5. That says that A is 5. At the rate of 0.2 cubic meters per second. Okay, that is going to be the volume of water per time. So that tells me that dv dt is 0.2. Okay, so volume with respect to time, that's the derivative of the volume, 0.2. How fast is the water level rising? That's dh dt. When the water at the moment is 4 meters deep. That means that h itself is 4, and we have to find dh dt. So you just plug in all that stuff. So we leave the dh dt alone because we don't know what that is, but we plug in 4 for h, the 0.2 for the dv dt, and 5 for the a. All right, and then we just simplify the stuff down until we get dh dt by itself. So 40 minus 16, I think, is 24, and we're just going to divide that 24 over. So whatever that is, right? 0.2 divided by 24 and simplify that down. I'll do it in my calculator here. It says it's 1/12. So 1 over 12 pi. That pi is in the denominator. Just to type it in. Oh no, I messed up somewhere. I did something wrong somewhere. Another like little mistake. Oh, I did the 1/12 wrong. It shouldn't have been 1/12. It should have been 1 over 120. So 1 over 120 pi. There we go. Okay, so this was meant to be a hard question. Not something that I would expect you guys to get like first try right away. It's kind of a thinker. But just know that you may have these caliber of questions on tests in the future, and to be ready for them. It's still using the concepts that we did, like the disk method, but just taking it kind of one step further with some old Calc 1 level material. Is this one all right now that you've seen this with the implicit differentiation and just plugging in the given values? Is there any question about how that worked out? Okay. Great. There was one other one that I want to show you, and I might show you this one just real quick. It's in section 3, I think. Let me just find it. I just want to show you this one because the antiderivative can be kind of hard. I just have to find it. This one, I think. So this is number 2 on the section 3-4 homework. And like I said, I know it's getting kind of late. It's almost 2. So we'll just do this one, at least get it started so I can show you what it is that you have to do. I'm sure that most of you haven't quite made it to this section, and that's okay. I just want to show you the little trick that you need to do here. So the question is to find the length of the curve x equals y cubed over 27 plus 9 over 4y on the interval 3 to 5. So this is arc length stuff. And there's just an easy formula to it. The length is going to be the integral. So for us, it's going to go to 3 to 5 of the square root of 1 plus the derivative of the function squared. Dy. I'm doing this with respect to y because they give it to me as a function with respect to y. Normally it would have x's in here, but it honestly doesn't matter. So this is the formula, and you'll be given this formula. It's on the formula sheet. It's not hard. The hard part is that when you do have to find the antiderivative, that can sometimes be difficult. First thing that we would have to do before we even plug it in here is to figure out the derivative of this with respect to y. This first term, we're just going to bring down the 3. It's going to be y squared over 9. This one, you can think of it as a y to the negative 1. So we're going to bring down that negative 1, and then it's going to go to a y to the negative 2, or a y squared on the bottom, like that. All right, so 9 over 4y has derivative negative 9 over 4y squared. I did that pretty quick, but just make sure you can get to that. Then when we plug it into my integral, still the integral from 3 to 5, still has the square root. It's going to be the 1 plus this derivative that we just found, all squared, dy. All right, so just substituting in the derivative into the formula here. Still going from 3 to 5. We'll go ahead and square that off. We're just going to FOIL that all together. So y squared over 9 times y squared over 9 is y squared over 81. When we multiply these two things together for the inner and the outer, the y squared cancels out top and bottom. The 9 cancels out top and bottom. We're going to have a negative 1/4 for the outer and a negative 1/4 for the inner. And then the two last is just going to be this thing squared, which is positive 81 over 16 y to the 4th. Okay, so that all with a dy on the outside. So these four terms was just foiling out this parentheses. Simplifying it down, we still have the integral from 3 to 5 of the square root. We have a bunch of constants, right? We have a 1, we have a negative 1/4, and another negative 1/4. Those three things add together to be a positive 1/2. And I'm going to write that 1/2 in the middle. So we still have the y squared over 81. It's going to be a positive 1/2, and then the positive 81 over 16 y to the 4th. Now the reason that this one works out, and this is the hard part here, this is the part that most people don't see. I wouldn't see it if I didn't already know how to do it. Oh, sorry, this should be a y to the 4th up top here when you multiply that together. Y to the 4th over 81 when you square y squared over 9. All right, the trick to this is to notice that these three terms together are pretty much exactly the same as what we had before. It's just instead of a negative in the middle, it's a positive. So these are going to factor, instead of y squared over 9 minus 9 over 4y squared, it's going to factor into y squared over 9 plus 9 over 4y squared. All squared. Okay, and then that's pretty much it. From here, you have a squared inside of a square root, which is going to cancel out. So you still have the integral. Still going from 3 to 5. But now the square root and the squared cancels. You have the y squared over 9. There you go. And then plus the 9 over 4y squared. And then these are easy enough to find the antiderivative for. So just find the antiderivative, plug 5 into it, minus find the antiderivative, plug 3 into it. Okay, cool. Yeah, so that's it for that one. That's the trick for it. So I just wanted to show you that before you got to it yourselves on the homework so you would know what the trick is. Is that one all right? Does that make sense on how to do that? Any questions? Okay, cool. So I really only want these to be about an hour long each time. So is there any last questions before I let you guys go for the week?
I'm good.
Cool. If you do run into any other problems as you're working on the homeworks until Sunday, feel free to email me, and I'll try to help you out through email. But we can set up another session like this if you just want to do kind of like a one-on-one thing where I show you how to work through a problem. I'm here for you if you need the help. So if you run into issues, just email and ask. Other than that, though, let's head out for the day, and we are going to have another one of these Tuesday at 6 p.m. So I hope you guys can make it to that one.